Hello friends, today we're going to talk about a couple of power supplies that I got as e-waste. These are both Samlex RPS 1204s. It's 13.8 volts output with a DC with a 120 volt AC input. Um, this one is complete, but it's been kind of dropped and had some damage. This one has been partially gutted, but there's still one thing inside that's of interest to me. So we'll talk about that next. This is a shot of the inside. It's a linear power supply, which means that it starts with a big transformer, convert our input voltage of 120 AC into something close to the output voltage of 13.8 volts. So the board provides a couple of important functions. At a real basic level, we have a couple of diodes to rectify the AC into DC coming off of the transformer. We have a smoothing filter capacitor. I don't know if you can see that. Miscellaneous components. This, I'm guessing, is a regulator or power transistor of some kind. And then we've got this big power transistor on the outside with its associated heatsink that's basically doing the final regulation for us with the under the control of this little board here. So that's kind of a real quick view of a linear power supply. Now this is the second one that's been gutted, and for whatever reason the previous owner decided to leave the transformer but take the control board and guts out of it. And that's okay for my purpose because I have a plan for the transformer. But the key point for our purpose here is we've got two of these big transformers to work with. And I'll tell you my plan for those in a moment. But now in this one, I've already tested out a little bit enough to know that the transformer works, the rectifying diodes work, but no voltage comes out of it. So this is truly dead. This type of power supply is basically obsolete now. Linear power supplies of this capability are kind of not really manufactured anymore because it's cheaper to, they still work fine if it's in good condition, but that it's basically cheaper to make what's called a switch mode power supply, which is kind of an entirely different design. So currently the common design for this type of thing is a switch mode power supply, which have now become more economical to produce for the same specifications. And one of the reasons that these are kind of expensive and heavy is we got lots of copper inside here, and copper has gotten increasingly expensive over the years. This is a switch mode power supply that's kind of comparable. I believe this one is 13.8 volts, but notice this, 15 amps versus, let's call it 5 amps here. So this is about the same, or actually smaller and lighter, but it has approximately 3 times the current capability at the same voltage. So, you know, unless it's actually more expensive, which, as I said, it's not, there's really no reason to use this type of design anymore. And switch mode power supplies have kind of taken over the world, whereas they used to be this type of linear regulated power supply. I think this one is approximately, 10 or 15 years old, maybe even 20 years old. So that's our tour of this power supply, and we're going to talk about next what I want to do with that. One of the things I need for my lab work here is an isolation transformer, and what that is basically a transformer that takes in 120 volts, puts out 120 volts, but is electrically isolated between the input and output. So it's basically a one-to-one transformer. And you can buy those for approximately $100 new. I kind of didn't want to spend that much money, and I don't need anything real fancy. So one thing that you could do in this case, let's say you have two identical transformers. We're going from 120 volts to say 13 volts to round it off. Then if we can go to 13 volts back to 120 using two transformers, we've got a system that's provides isolation capability and basically has the same total power rating as either one of these individually. Now that isn't really a great way to make an isolation transformer for production use, but for my purpose where the materials are free, having two transformers doing that job instead of a single transformer is more economical for me because these are free. And if you multiply the, let's call it 5 amps by the 14 volts, so we get about, what's the math on that? Help me out here. 5 times 14 is 70 watts. So that I can push 70 watts through this transformer and through the same 70 watts through its twin there. And so long as I'm not pulling more than 70 watts total power on the output, I'm good. And also we've got some other little features here that are going to be helpful to me. We've got a fuse, we've got power switch, and you know, a nice little chassis that I can maybe mount a kind of a standard wall outlet type thing in. I can kind of imagine, you know, cutting this out and putting a wall outlet in that space. So we'll see how that goes. Now we're going to talk a little bit about the transformer here. One of the problems of construction of a transformer is you have to wrap the wire around this inert part, which is called a bobbin. And for production purposes, that needs to be done at high speed. But this is totally surrounded by this iron core, so what they typically do is have a set of plates that sort of squeeze together around a pre-wound bobbin. And then you have different ways of keeping the plates together that need to be, you know, in physical contact, and the closer the better for more or less squeezed tightly. Sometimes they have screws in the corner or rivets or whatever it is. In this case, I'm guessing we're going to find out that this is actually loose inside this enclosure, and that this enclosure here is not just holding down the transformer, but it's actually holding it together. So let's pull that apart real quick and we'll see what we've got. Now it's time for the big reveal. I'll take the last screw out here. We're going to find this out together, what we've got. And let's see. So looking at this, it appears to me that it's not physically held together by a screw or whatever, and so it looks like I was kind of right and kind of wrong. This really is holding it together in a strict mechanical sense, but there's some sort of coating or whatever that's kind of giving this a basic mechanical shape. So probably enough for, you know, assembly purposes to get it into the frame here. So we've got a similar one in the other one. I could potentially fix this one, and I've considered doing that, but since I've got some better ones and you only need so many of these things, I'm not even going to bother to try to fix this. Well, here's the patient after I got everything taken apart. Here's the control board. Turns out it was riveted in, so I had to drill out the rivets. Here's the heatsink and power transistor assembly, some miscellaneous screws, and I kept a lot of it intact, the power switch, the fuse, and the rest of it. So now I've got the second transformer here. To give you an idea, we've got 3 wires that this corresponded to the 14 volt center tapped output of each transformer. So we connect the corresponding 3 wires here, and we've got, they're kind of short and clipped off, but we've got what would be the 120 volt input wires for this transformer on the other power supply. But in this case it'll be the 120 volt outputs on this side, and we'll have 14 in the middle center tap that we may or may not use. But you can imagine from this end with a 3-prong outlet, this end we only have 2, which is the chassis ground. I haven't figured out what I'm going to do about that yet, but I think it's looking like it's going to be just open on the output side. And because of the fact that these things are only coupled through the magnetic action of the transformer, there's no, when this is finished, there's going to be no electrical contact between our hot and neutral on this side and hot and neutral on this side. So for our next step, we'll begin wiring some of that together and figuring out how to work up the mechanical aspect of it. Before I go any farther with this, I need to check that the transformer is working correctly. And as a kind of a pre-step on that, I believe these wires still have enamel on them. So transformer wires have enamel around the, which is an insulating material around the wires, and you'll see with my voltmeter that I've got, you know, an inconsistent reading there. This one may be open. So I've got enamel still on the outer edges of all of these wires. So I've looked up on the internet the way to remove enamel. There's multiple ways to do that, and I'm going to try out some of those next. First I'm going to try just scraping off with a little cheap utility knife. Try that one. Another technique I saw mentioned was using sanding of some kind. This is a sanding sponge. Oh, that's probably hard to see in the video, but there's a color difference once the enamel is removed. It kind of gives you a good idea that you've been successful. Another method to use a wire stripper is kind of a scraper. So I'm going to try that on the third one here. That isn't working real well, and I think you also have the risk of damaging the wire, which I can see I did a little bit of there. Another technique that was mentioned is melting off with a soldering iron, but that might leave a residue, so I'm kind of thinking that generally speaking the scraping technique is a good starting point, and then maybe when I solder the wires later, that'll kind of finish the job. Okay, so with that done, I should be able to touch near the ends of this and get a, we can do a diode test thing, which makes a beep on this meter. So I've succeeded in scraping off the insulation, and just for comparison, if I go further down where I haven't scraped it, I've got nothing. So that it all fits together. This one might have a nick on it or something further down. So next we're going to be ready to do a little voltage testing coming off of this. Get everything plugged in and rigged up. I'm got the voltmeter on AC setting. I'm I'm connected with the ground of the voltmeter to center tap, and then I'm going to touch each of these two after I turn things on. Should get about the same AC voltage, which I'm expecting to be in the 14 volt range or maybe a little higher. So I got a power supply or power strip over here. Turn this on, being careful not to touch anything live inside there. And let's see what we have on this side. Okay, 18.9 volts about. And $18.9 volts. So that's kind of what we've got in the middle here. So what we know from this is that the transformer works, the stripping of the enamel worked as intended, the other basic things like the switch and the fuse all work, and this is ready to go for the next step. All right, we're ready for the next test. We've got, it's a little hard to see here, but I've connected the 3 corresponding leads of the 2 transformers on what would have originally been the output side, which is the low voltage side. And then on this one, which would have previously been the 120 volt input side, I've connected my voltmeter and got it all connected in advance, so I don't need to worry about being in contact with 120 volts that I'm expecting to come at this point. So kind of to put it in perspective, we have 110 coming in here. We have this 20 something volts AC coming out here, going in here, and coming back out as 120 volts. So we'll turn it on and see what happens. I'll turn on the power strip. I've got kind of a double switch set up here, and turn on in 3, 2, 1. Okay, so that's all a success, 118 volts. And that shows us, to put in perspective, I assumed but didn't really know that this second transformer worked. If you remember, it came in the box with everything else taken out. So, who knows what the person who had it before was thinking, but anyway, it could have been that this transformer itself was bad, and that was the reason to throw it away. But it turns out this is good, and it's the fact that it's doing 118 volts here is, here comes Polly, she wants to help. Here, you can get in the shop, Polly. The fact that it's doing 118 volts here is what we need at this point. I better turn it off before the cat shocks herself. She's had enough of that with just static electricity, right, kitty? I've rigged up a comparison of the input voltage versus the output voltage. This one is showing 121.5 volts coming in. We're going to turn on our system again to see what's coming out. 118 volts coming out, so that makes sense. We've got a little bit of voltage drop due to the resistance of the wires inside the transformers, and there's also some losses associated with the magnetic action of the transformers. They generate a tiny amount of heat, so that all makes sense. So this is still a success because the drop is pretty small, and the fact that things that use AC wall voltage are tolerant to fluctuations of a small amount, which happens in the power grid in general anyway. It's not a big deal. 118 volts versus 121. Most things that are run on this type of voltage say 115 to 120, so that's well within range. So everything's adding up. We have ready to kind of move on from this jury rig setup with a bunch of alligator clips and into something that's a little more sturdy and stable for future lab use. So the next thing I've been working on is the kind of mechanical arrangement of how things will be bolted together and kind of getting some idea of what the finished unit would look like. Um, it seems obvious to me that we want to reuse these cases. I've got them propped up on their lids at the moment, but as you can see here, we're going to have the 3 corresponding wires wired together with some insulation and heat shrink and so on. These 2 areas will be combined. Let's talk about grounding real quick. We've got this pin, which is earth ground. That goes to this mechanical connection. So if I connect this in the chassis like so with a hole cut out, chassis are connected together. This chassis is already connected to the corresponding ground pin on the 3-wire cord. And we'd have our entire chassis earth grounded. And that's okay because what would be the hot and neutral at this point, it isn't really neutral anymore because it's isolated from earth ground. So these are kind of 2 independent and interchangeable AC connections at this point. And that's really the essence of what we're trying to do with this isolation transformer. Is we're trying to create a 120 volt signal here that is not referenced to the earth ground here. And that has some uses in electronic troubleshooting and so on. So what I'm envisioning doing here is cutting out a suitable hole, maybe making it pretty with a wall plate if I can, if there's space. May remove the fuse to make a little more space, and then you can imagine having a nice little combined system that has 2 plugs on it for general use as an isolation transformer. Here you see some markings I've made. I basically put the wall socket upside down, traced around the edge of it with a marker, and this kind of gives me a rough guide on how I'm going to cut out holes for this. I decided to try to preserve the fuse, which kind of put me in the spot that I'm in there. So I also think to make it look nice, I'll ultimately put a plate on top of it, but we'll see how that goes. I'm not really well set up to cut this type of metal. I've got a drill press that's kind of on the small side. We're going to figure out how to do that some way or another. Got hacksaws. It's just going to be a matter of figuring it out based on what I've got. So after thinking a little bit about how I might cut out the kind of complicated hole pattern I had before, I realized I'm not really set up to do that. And also, I'm going to want to put a wall plate on here anyway. So I decided to scrap the fuse, or maybe relocate it if I use one. I really don't necessarily need one at this point. But fit the wall plate on there like that. That allows me to cut out a rectangular hole here, which I am equipped to do with these shears. So we'll do that next. So this is pretty easy to cut with these shears. Okay, so let's do a rough fit on that to see if it's working. Looks like it is. Do a little touch-ups. Go from there. Okay, I think that's going to be a good starting point, and then we'll work on the parts of mounting the wall socket and the plate as our next step. Well, I've got this all set up and pre-marked. I'm going to drill some little pilot holes here to start with. So about an hour after the last shot, I finally got this done. I found out there were 6 different ways to do this wrong, and I found all 6 of them. The last one was I forgot to put lock washers underneath here, but I did that. And got our electrical cable pre-installed, ready to go for the next step, and we're ready to put in the transformer and begin joining the 2 chassis together. Well, I got the transformer put back in, and I screwed the 2 chassis together with the screws that came with them. That makes them go in backwards in both cases, but with this type of screw, it's kind of a self-fitting sheet metal screw. That works. It isn't really very strong, so I'm probably going to have to supplement this in some way with maybe another nut and bolt screw, maybe up here. And you can see we've got our 3 wires in the center. I haven't connected those yet. I've got my 2 front banana jacks available that I may connect to the middle section, so we can get AC out of the middle if we want to at the low voltage. But there it is at the current state, and we'll keep going and see what happens. So before I connect all the wires together, I thought it'd be good to probe them on the scope here real quick. I've got the ground wire of each probe on the center tap, and I've got 1 channel on each. So you're seeing on the scope screen /60 sine wave out of phase between the 2 channels, so that's what we expect. So everything there is good, makes sense, and we're ready to move on to connect the 2 transformers together in the middle of the assembly. Well, meanwhile, I've twisted the center wires together here. It's just a friction twist. I put these little insulating sleeves that came on with them before. That kind of protects the enamel from getting nicked, inside the chassis. Got it turned on. We're reading 119 volts at this point. And for comparison, again, back at the wall, we're getting 122 volts in, so that's about similar to what we had before. So everything looks good. I'm ready to solder the center wires together, put on some heat shrink, and then I'll be working on this left section, which will be our output. Basically, I just need to take this wire that's already wired to the power outlet on the front and kind of shorten it and wire it to these 2 here. I've gone ahead and soldered these 3 wires in the middle and cut them down a little bit. I soldered the 2 on the left that go to the outlet and pre-positioned this heat shrink on them. So now we'll do one final test before we button it up. Okay, 117.6 volts, that's good. Now we'll move on to the heat shrink. And with a wave of my magic wand, magic. And again, our magic wand. So here's kind of a panoramic shot of the inside now. We've got heat shrink on both. I've left the chassis ground for the outlet unconnected for the moment, and may leave that forever unconnected because it really doesn't serve any function on the output side of an isolation transformer, but the wire is still there if I decide to connect the chassis. Now we're ready to continue with some of the mechanical issues of getting the lid on and making it a sturdy box. So mechanically right now all we've got is these two screws here and here holding the two chassis together, and that's okay for kind of work use, but it's really not a long-term solution. We want to make this kind of one solid unit. So the plan I have, there's a couple of things. One, I've got some strapping that'll go underneath here, and it turns out the spacing on the strapping in these screws is standardized, so that I'm going to put one piece of strapping here, another one here, and that'll make the bottom side a single rigid element. So I'll go ahead and work on that now, and we'll show you the results shortly. Do one final tightening. All right, so now our box is pretty good mechanically as far as the bottom goes. The next step is going to be to join the tops. So my plan on these is to basically join the sides here. I've got some existing holes that were originally air holes. I'm going to put in some nuts and bolts in there and cut off the bottom to allow this to fit over the top as one piece and not hit the connections in between the two transformers here. So we'll do a little cutting and get it all put together. Now I've worked out in advance that I need 3 rows of holes here to get the right height. So I'm just going to cut to get the 4th row off. Okay, we're done with that. Do a little bit of straightening out and put some bolts in it.
And the Oscar goes to...
Got the screws put together into this. Did some extra cutting. It turns out my side tabs idea didn't work. I had forgotten that these enclosures go just a little bit over the top of the chassis. So now we've got a nice fitting unit on here. And we can line up our screw holes there and put in some of the remaining screws. See, I'm missing 2. I've got 2 screws loose, not just one, but that'll be enough to give you the idea. So let's look at the finished product before we try it out one more time. Straps on the bottom. Got two pieces on the top that I turned into one piece. When I get all four screws in, we'll have structural support across the top. We've got a screw here and corresponding spot in the back, which I'm not relying on a whole lot, but it just kind of adds to the overall picture. And the idea is that this is and should be a real solid unit. It's pretty heavy due to the transformers, you know, guessing 5 or more pounds. But we're all ready to go. So let's try it out next. This isolation transformer, by my count, should cover about 60 watts because it was designed for approximately 12 at 5 amps. So that's 60 or maybe a little more. Now we're going to do a little bit of load testing. I've got this turned on, showing 119 volts there. This is a 5 watt LED lamp, as in 5 actual watts. We go down to 117 volts here. We're reading about 9 watts. So I guess the bulb was a little bit off. Let's try it next with an actual 40 watt bulb. So again, 119.3 here. I've got a 40 watt incandescent bulb in here that really should draw approximately 40 watts. Turned it on. We dropped to 110.7 here. And an actual wattage of 34.9. So that's probably makes sense that the voltage is down a little bit lower than rated. The bulb actually says 120 volts on it. So it would draw a little fewer watts with fewer volts to work with. Polly, do you think that was a success? Polly approves.